Hello. So, what are we looking at here? Well, we are looking at a website or a web page that is reviewing a text adventure that I helped work on. So this game was written by a developer who lives in London, Quantum Sheep, and he released his game or put it up on itch.io. And here it is being reviewed on a Portuguese website. Now, the computer that he released it on, the Spectrum 48K, was very popular in Brazil, and that is probably why this page is in Portuguese. Although you could translate it into anything else. Now, George thought, well, that's Quantum Sheep's real name. He thought, okay, well, you know what? Wouldn't it be really cool if we could get this thing running on the Commodore 64? So let's look at what a Commodore 64 is. A Commodore 64 was kind of the dominant home computer of the 1980s. It was made from, I think, about 83 to 93. They made about, I think, 20 million of them. It was one of the most widely manufactured computers ever. With the possible exception of the Raspberry Pi. And it's been re-released lately as the C64 Mini. There's kind of a little miniature version of it. And now they're re-releasing a full-size version of it, but with all the modern bells and whistles, USB, HDMI. You don't have to deal with floppy disks and RF outputs and stuff like that. So the trick is, okay, how do we get that text adventure and get it into a Commodore 64? So now we tried to do this and we ran into some snags, and let's talk about those snags. So to figure out what problems we're going to have here, there it is running in the Commodore 64, but let's not jump to that. So we can see here that his program is 41,962 bytes long, so almost 42 kilobytes of data. Now let's look at the memory map for a Commodore 64. So remember that the processor can see a certain amount of memory based on how many pins it has. And remember, from hexadecimal, a hex F is 1111. So this processor has 16 address lines. So the highest address it can see is 1111, 1111, 1111, 1111, which is 65535 in decimal, but we call that 64K in computer lingo. Now, let's see how much memory is available for his program. Now, RAM for a user program, starts at hex 1000 here, and it goes up to 9FFFF, at which point the next chip above that, it contains the basic ROM, and that's the programming language that's built into the computer. That's like Python. So we have addresses. We can put a program somewhere between 1000 and hex and 9FFFF and hex. So let's just pop over to the Microsoft calculator here, and I'm going to put it in programmer mode. Normally it's like standard mode, but you can go into programmer mode, and this is super cool. So let's see how big that is. 9FFFF. Well, we can see what this is going to be. 9FFFF minus 1000. We can see that's going to be 7FFFF, right? 1000, 7FFF. Excuse me. And so you can see that 7FFF in hexadecimal is 32,767. So about just under 33 kilobytes, right? So how are we possibly going to get a program that's 42 kilobytes into that space? Well, and that brings up a very interesting question. So let's go back to this diagram, and you'll notice here that for certain address ranges, there is more than one possibility. So for like this bottom 0 up to FFF, there's RAM, right? And from 1000 up to 9FFF, there's RAM. But between A000 and BFFF, there's two possibilities here. We have RAM or the basic ROM. And then above this, we have RAM or the character ROM, which is the font, or RAM for I/O. And then at the top of memory here, we have RAM or the kernel ROM. The kernel ROM, think of that as your BIOS. So what we're going at here is the processor can only see this window between 0 and FFFF. However, within that address range, right, within certain address spaces here, we can switch in or out which chip we want the processor to look at. So what we want to do is drop out the basic ROM, which is the default setting, and switch in this RAM chip. We want to disable this ROM and enable this RAM. This is called bank switching. So notice that we have, basically you could think of these vertical stripes here as memory banks, right? Which bank of memory do we want to use? We don't want to use the basic ROM for our program. We want to use the RAM. So that's called switching in the RAM or banking in the RAM. We want to switch out those chips. And if we did that, then we would have RAM all the way up from 1000 all the way up to CFFF. And let's take a look at what that would get us. So that would be CFFF minus 1000. You can see that's going to be BFFF, I think. But did I get that right? Which is, oh, look at that, 49,151 bytes. More than enough. And that is how we got this to work, right? So what we did was drop out the basic ROM, switch that out, enable the RAM chip in that address range, and now we have more RAM to play with and we can do that because we don't need what's in that ROM chip when we're running this game. Now, the takeaway here is that the Commodore 64 can see all of this memory. It just can't see it all at the same time. So the processor, you can have a program that can look at the kernel ROM and it can use this RAM, but it can't use the kernel ROM and this RAM up here at the same time. So you can bank switch in and out. You just can't have them running at the same time. And this trick of bank switching allowed these 8-bit computers to see fairly large amounts of memory. So for the Apple II example, there's a card called the RamWorks, and that card allows that has a megabyte of memory on it. So imagine an Apple II with a meg of memory. That's crazy, right? But that's what bank switching allows you to do. It allows the processor to see much more memory than can actually fit into its address space. It just, now the trade-off is that it just can't see all that memory at the same time. Now, for games, this is very, very important. So let's look at Legend of Zelda here, classic NES game. This game is huge. It goes on and on and on. And how did they fit such a huge game into such a relatively primitive console by today's standards? And that is bank switching. The cartridge has banks of memory on it, and the programmer can configure which bank of memory the processor is actually looking at. So even though that CPU in that NES is the same as in the Apple II and the Commodore 64 and basically the Atari, it can see much more. Using that trick of bank switching, you can have a game that's about a megabyte, even though the processor can only see 64 kilobytes. So that is what bank switching gets you. It allows your game to be much, much bigger than, to take up much more memory than the CPU can actually see. Now, the only trick is that the CPU can't see all of your program at the same time. So that's what bank switching is. Now, if you were actually just sort of wondering, how do you switch banks? How do you actually control that? Well, that has to be designed into the hardware. So on this Commodore 64, way down here, actually it's address 1. If you write to byte 1 of memory, which is the second byte of memory, you can actually, depending on the number that you put in there, it is used to toggle on and off these different chips. So by writing, as the programmer, if you write to a particular address, way down in the computer's memory, you can configure how this memory which banks of memory you are enabling and which banks of memory you are disabling. But I don't know, cool trick there, and that is what enabled us to get Seance running on the Commodore 64.